Let's solve this angular momentum problem. So we have a 50 kilogram child on the edge, so it's going to have the same radius, as a 60 kilogram spinning disk with a radius of 3 meters and is spinning at 4 meters per second, or 4 radians per second. What is the total moment of inertia of the system? So this is when we need to find the moments of inertia of both the child and the disk. So we look at our chart. The child is going to be a satellite because he or she is a point mass spinning around the center. So the moment of inertia is going to be mass times the radius squared. We can also look at our chart and see the moment of inertia of a disk is 1/2 mass times the radius squared. So we just plug in the numbers. So we get 50 kilograms times 3, because that's our radius for both, 3 squared, which of course is 9, and we get 450. And then we take 60 kilograms, or 1/2, times 60 kilograms, times 3 squared. So that's 9 times 60 is going to be 540. 1/2 of that is going to be 270. And we simply add them together to find the total moment of inertia, I total, and that's going to be 720. What is the total angular momentum of the system? Well, angular momentum is, of course, L equals our moment of inertia times our angular velocity. So in this case, it is going to be 720 times 4 radians per second from up here. And that's going to get us 2,880. The child walks to 1 meter from the center of the disk. So our new radius for the child is 1 meter. Assume angular momentum is conserved, so we're going to keep this angular momentum. What is the new angular velocity of the system? So this is when we use this formula, L equals I omega, the moment of inertia, times the angular velocity. And we do some algebra to rearrange it. We get omega, our angular velocity, equals our moment of inertia, equals, our angular momentum, divided by our moment of inertia. And so this is how we will calculate our new velocity with this angular momentum, which is going to be conserved, so it's going to be the same. Now we've got to find the new moment of inertia. So we've got to find the total moment of inertia with the child 1 meter from the center of the disk. The disk's moment of inertia is not going to change. Because nothing about the disk changed in the problem. So that is still going to be 270. The child's moment of inertia, however, is going to change because the child is now only 1 meter from the center of the circle. So we go mr squared, and we are going to take the mass of the child, which is 50 kilograms, times our new radius squared, which is 1. 1 squared is, of course, 1, and so our new moment of inertia for the child is just 50, which means our new moment of inertia total is 270 plus 50, which equals 320. Now we can use this formula here to find the new angular velocity. We take the angular momentum from the previous problem, or from part B, which of course is conserved, and then we divide by our new moment of inertia, which is 320, and that will get us our new angular speed. 2,880 divided by 320 gets us 9 radians per second.